Welcome to the first lecture on probabilistic method. This was a method pioneered by Paul Erdos, and it has found a lot of applications in combinatorics and computer science, theoretical computer science. We shall begin by discussing two problems. One is the lower bound for the diagonal Ramsey number and the second problem that we will address today is the lower bound for the size of the maximum cut in a graph. Okay. So, we shall learn probabilistic method by means of many examples. These are two simple problems for which probabilistic method gives reasonably interesting bounds. Okay. So, let us understand what is this diagonal Ramsey number. So, consider any graph G. Okay. So, this graph can, so we are looking for two substructures in this graph, one being a clique and the second being an independent set. So, a clique is a set of vertices such that, so if G equals V, you take a subset of vertices such that all of them are connected to each other, that is called as a clique. For example, if we look at this particular graph with 6 vertices, and if I look at vertices 1, 4 and 6, they are all connected to each other, that is going to be a 3 clique. So, that is a clique of size 1, 4, 6 forms a clique of size 3. Okay. You can simply say that K3 is present. K3 is a complete graph on 3 vertices as a, so we can say K3 is present as a subgraph of G. If we had, let us say, 2 connected to 4 and 2 connected to 6, then 1, 2, 4, 6 forms a clique of size 4. So, that is the definition of what is a clique. Now, if you look at 3 vertices 1, 3 and 5, you can see that it is in some sense a complement of the clique. None of those edges are present. 1, 3 is not an edge, 3, 5 is not an edge and 5, 1 is not an edge. So, those kind of collection of vertices are called an independent set. So, an independent set is a collection subset of vertices of the graph such that for any 2 vertices in that set, they are not connected by an edge. So, that is an independent set. So, let us now define what is called as the diagonal Ramsey number. Okay. So, consider any graph G okay. So, this graph may contain an independent set. G may contain an independent set of size, let us say S, or may contain a clique of size T. Okay. So, we are interested in finding, so this is not, I mean if you take an arbitrary graph it may contain neither, but we are looking at the smallest number n such that if you take any graph with those many vertices, it will either contain an independent set of size s or a clique of size t. Okay. So, will there exist such a number? If there is one such number, let us say if you take, let us fix s to be let us say 3 and t to be 3, what sized graph should we take so that it will invariably contain either an independent set of size 3 or a clique of size 3. Okay. One can show that if you take a graph on 6 vertices, this property will be true. So, let us just quickly see that. So, let us take any graph on 6 vertices and let this be one of the vertices of that graph. Okay. Now, there are 5 other vertices, namely 1, 2, 3, 4, 5 and 6. Now, out of these 5 neighbors or 5 vertices in the graph, one may be connected to 3 of them or may not be. That is, I mean, so we can write the following: either there are 3 edges out of 1, or there are 3 non-edges. This is because the total number of vertices are 5. Okay. So, number of edges plus number of non-edges is going to be 5. So, one of those numbers should be at least 3. So, let us without loss of generality assume that this is, there are 3 edges. The non-edges case is exactly similar, it is a symmetric argument. Okay. So, let us say these 3 edges were present. Now, if either 3 and 4 are connected, if, I mean, let us look at these dotted edges, I mean, they are not edges, let us consider those pairs of vertices. If even one of them is present, you automatically have a clique of size 3. So, in order to avoid a clique of size 3, all those 3 have to be not present, in which case they form an independent set. This tells us that if you take any graph with 6 vertices or more, it will invariably contain a clique of size 3 or an independent set of size 3. We will generalize this, okay, and instead of talking about independent sets and cliques, we will talk about coloring the edges. You may think of it as the edges that are present have been colored using one color, and the edges that are the pair of vertices which are not connected, they will be colored using a different color. So, we will state the definition of Ramsey number in terms of coloring. So, Ramsey number RST. Okay, so, this is defined as the Ramsey number RST is the smallest n such that any coloring of the complete graph on n vertices will result in a subgraph of, say, subgraph Ks. So, that is a complete graph on S vertices such that Ks is colored So, we are coloring, so this any coloring, here we are two coloring, any two coloring is colored, and we will assume without loss of generality that the colors are red and blue is colored. So, there is a subgraph such that is colored red, or there is a subgraph KT of color blue. Okay. So, the smallest number n such that any two coloring of the complete graph on n vertices will result in either a subgraph of size S which is colored red, or a subgraph of size T which is colored blue. Okay. So, clearly if there is, I mean this set of numbers which satisfy this property, they will be, I mean if n is present, n plus 1, n plus 2, all those things will be present. The smallest such is what we are interested in. Okay. So, it was shown by Ramsey that, so Ramsey's result is that RST is finite for every S and T. Okay. So, now what we are interested in is how large will RST be. What is known as, so we have right now seen that R33 is equal to 6, R44 has been shown to be equal to 18, R55 it is not yet, the exact value of R55 is not known. It is known that it is between 43 and 48. Now, how do we determine R55, or for that matter any RKK? So, when S and T are equal, that is what is our diagonal Ramsey numbers. So, how do we determine RKK? Okay. Exact values is very difficult even for small values of k. So, can we bound it? If we were thinking about computing RKK, what should we do? How expensive is it to compute it using computers? So, let us just look at the following. Let us take a graph on n vertices, okay, complete graph on n vertices. So, there will be n choose 2 edges, and we will try all possible colorings. So, that is going to be 2 raised to n choose 2 colorings, 2 raised to n choose 2 colorings. We will try all possible coloring. If we can find one coloring such that it avoids the red clique of size S and the blue clique of size T, then we know that RST is going to be greater than that particular n. Okay. Clearly, we cannot carry out this computation, because even if let us say n is say as small as 5, this gives us 2 raised to 5 choose 2. So, 10, sorry not, so this n is the number, I mean, so here the R55 we know it lies between 43 and 48. So, if we were to try to check if R55 is greater than 43, we could take the graph on 43 vertices and color it using all possible colors. That will give us 2 raised to 43 choose 2 colorings. Okay. That is about, you can say it is at least 2 to the power 200 different colorings. Okay. That is prohibitively expensive. So, 43 into 42 by 2, that is 21. So, 43 into 21, these many colorings are there. $86. So, we can't really run a brute force algorithm to check whether RST is greater than a particular n. Okay. So, we will see how probabilistic method can be used to show that RST is at least greater than a certain number. Okay. We will use it to obtain lower bounds. Okay. So, let us see how this lower bounds is obtained. So, this is the kind of problem that we are interested in. So, we have a combinatorial property which is captured in terms of this, let us say RST. Okay. So, is there a graph on n vertices? So, if you take the complete graph on n vertices, can you obtain a coloring which avoids say cliques of size S which are monochromatic or cliques of size T which are of the other color. Okay. So, this is the kind of property that we are interested in, and we will use when we use probabilistic method, typically the proof proceeds in 2 steps, 3 steps. First, we will have to set up an appropriate probability space. And then we will sample from this probability space and compute the probability of an event. Okay. And in third step we will compute the asymptotics. Okay. Initially we will go through all these steps one by one. Later on we will not explicitly do that. Okay. It will be, I mean, but essentially that will be the steps that will be that we will be employing. Okay. So, in case of when we want to obtain lower bounds for R kk diagonal Ramsey number, okay, the probability space is the following. Okay. So, let us look at the graph on n vertices, okay, and we will choose a coloring of these things. Okay. So, the sample space consists of all the possible colorings that we can obtain for this. Okay. So, what are the probability of each coloring? Well, we will assume that each edge, we are coloring the edges here, each edge is being colored either red or blue, and that with equal probability. So, that gives us the description of the probability space. Okay. In other words, we can think of this as, if you are given a graph on n, so we want to analyze whether n for some value, whether it can be an upper can be a lower bound for RKK. For this we will color the edges of Kn by tossing a coin. If the toss results in a head, then that edge is colored in red color. If it results in a tail, that edge is colored in a blue color, colored using blue color. Now, we can compute the probability of an appropriate event. We have colored this thing, this Kn randomly, and now we look at the following event. There, so let me describe a certain event. So 1, 2, 3, 4, 5, 6, these are the vertices. Let me look at some k of these vertices. Okay. Let S denote a subset of size k. Okay. Let ES denote the event that S is monochromatic. Okay. So, this will have a certain probability, and let E denote the event that there exists an S which is monochromatic. Okay. So, this is the event that I am interested in, and I will compute probability of E. If the probability of E is less than 1, then that means when you randomly color, there is a coloring which results in there being no monochromatic cliques. Okay. So, if we can compute this probability, or we can show that probability of E is less than 1, then that would mean that n is a lower bound for RKK. In other words, a graph on n vertices can be colored avoiding monochromatic K cliques. Okay. So, let us first compute that probability. Okay. So, this is our graph on n vertices. Let us look at this particular set S. Okay. It has k vertices in it. That means the edges, there are k choose 2 edges, all of them could be blue or all of them could be red. Okay. Let us compute the probability of that. Well, each edge is being colored independently of the other edges. So, if one of them is, let us say this is a red edge, all the others have to be colored in the same color if this has to be a monochromatic clique of size k and a monochromatic clique of color red. Okay, so, that happens with probability 1 by, so there are two possible colors that we could have, and each color, I mean each edge is being so probability that the edges are all colored with the same color is going to be 1 by, let us say all of them being blue happens with probability 1 by 2 raised to k choose 2, and the color could be either red or blue. So, there is an into 2. So, probability of the event E, okay, E was the following event: there exists a monochromatic clique of size k. Okay, so this probability is going to be less than union over all S belonging to Kn. Okay, we will look at all possible subsets, probability of Es, and that is equal to, so this is equal to, and that is less than by union bound sum over S belonging to Kn probability of Es. Okay. So, this is equal to, there are n choose, let us say, so this is a subset of size k. So, there are n choose k possible subsets that we could choose, and each of them, for each of them, this is the probability that it is monochromatic. So, 2 by 2 raised to k choose 2. Okay. So, this is the probability that this pair of vertices is monochromatic, that there exists a set of monochromatic edges. Now, if this quantity is less than 1, if probability of E is 1, so we can write this as a theorem: if probability of n choose k times 2 raised to 1 minus k choose 2 is less than 1, then R kk is going to be greater than n. Okay, so, that is our theorem. Now, we need to derive asymptotics, that is, for a given value of k, what is the best possible n that we can obtain. Okay, so, we will work out the asymptotics. Okay, so, our theorem was the following: n choose k times 2 raised to 1 minus k choose 2 less than 1 implies R kk greater than n. Okay. So, let us look at this quantity, that is going to be n choose k 2 raised to 1 divided by 2 raised to k choose 2 is k into k minus 1 by 2 is less than, this quantity is less than So, this is the n choose k, you can you can say that it's always less than n raised to k. There are k terms in the, when you expand it, there are k terms in the numerator divided by k factorial into 2 divided by say 2 raised to k square by 2, and there is a minus k by 2 which we will take up 2 raised to k by 2. Okay. And rearrange this and write this as n by 2 raised to k by 2. So, this we will combine, okay, that is what I am writing, n by 2 raised to k by 2 the whole raised to k times 2 raised to k by 2 1 plus k by 2 divided by k factorial. Now, if you look at this quantity, if n is, let us say, less than 2 raised to k by 2, or let us say floor of 2 raised to k by 2, 2 raised to k by 2 depending on k being even or odd may not be an integer. So, if n is less than 2 raised to k by 2, then this quantity is going to be less than 1, and 2 raised to 1 plus k by 2 has k by 2 terms, whereas this has k terms, most of them except the term 1 and 2, everything else is greater than 2. So, you can say that this quantity for reasonable values of k, this is going to be much smaller than 1. So, this overall quantity we can say that it is less than 1 if this condition is true. So, if, so you can write it as if n less than 2 raised to k by 2, then n choose k times 2 raised to 1 minus k choose 2 is less than 1. Therefore, we can say from the theorem R k k is going to be greater than 2 raised to k by 2. Okay. So, that is the first lower bound that we have obtained. You can use more complicated constructions and more complicated sample spaces to provide an improved, slightly more improved bound than this. So, now we will look at yet another problem. The next problem that we will look to illustrate the power of probabilistic method is something called as max cut problem. Okay. So, let us understand what is a cut. Let us take a graph. Okay, so, this is a graph with 1, 2, 3, 4, 5, 6, 7 vertices. A cut is a partition of the vertices of G. So, if your graph was G, a cut is a partition of the vertices of G into 2 non-empty sets A and B. Okay. Let us call them as A and B. There is also a different notion of an ST cut, in which case, whereas S and T are vertices, in that case we will insist that S belongs to one partition and T belongs to the other partition. But so, this is what a cut is. You could choose any collection of vertices and that will form a cut. For this graph, let us say we will look at vertices 1, 2 and 5. So, if we look at this vertices 1, 2 and 5 in one set, that forms a, I mean 1, 2, 5 in one being A and 4, 3, 6, 7 being the other set, that is our cut. Now, if you look at the edges of the graph, there are some edges which lie completely inside one portion, there are some which lie in the completely in the other portions, and then there are edges which go from one side to the other. For example, if you look at the edge 1, 4, okay, so 1, 4 is an edge which crosses the cut. That means one of the edges, one of the vertices of the edge is in A and the other is in B. These are what is called as a cut edge. So, a cut edge is an edge u comma v such that u belongs to A and v belongs to B. The number of cut edges in a cut C is called, so if you name the cut by C, the number of edges in the cut is called the size of the cut. Okay. So, here in this cut, the number of cut edges is going to be, so 1 4 is a cut edge, 2 3 is a cut edge, 3 4 is not a cut edge because these are both in the same component. Okay. So, here 1 2 3 4 and 5 6. So, there are 6 cut edges, you can verify whether it is 6 or something else. So, we are interested in finding, given an arbitrary graph, we are interested in finding the cut of the largest size. Okay. This is a computationally difficult problem, it is known to be NP hard, but can we find good approximation algorithms to compute the cut edges, the maximum cut? What bounds can we give to the size of the maximum cut? Okay. So, we will prove the following theorem. In any graph G equals B comma E, where size of, let us say there are M edges, there exists a cut of size m by 2. That means, you can always find a cut in any graph such that half of the edges cross the cut. Okay. Proof is very simple. Okay. So, we will just trace the steps of probabilistic method one more time. First, we have to design an appropriate probability space. Okay. The probability space for us here is going to be, we will choose the cut randomly. Okay. So, how do we choose the cut randomly? Each vertex goes into, so there were 2 parts A and B, and we have to obtain a cut. A and B, these A and B had to be chosen appropriately. So, we will randomly put a vertex into A or B. We will toss a coin, if it is heads, the vertex will go into A, if it is tails, it will go into B. Okay. So, this will clearly obtain a cut in the graph. Okay. Now, we are interested in the number of, so after this we have to compute a certain probability. So, what probability are we interested in? So, here instead of computing the probability, we will compute an expectation. Okay. When we take this random cut, how many edges are there in the cut? What is the expected? So, we will compute the following expectation. We will compute the expectation of the number of cut edges. Okay. And then we can reason that if the number of, if the expectation, if expectation of, let us say, if x is a random variable which denotes the number of cut edges, if expectation of x is greater than or equal to m by 2, okay, so of size greater than, okay, if expectation of x is greater than or equal to m by 2, then there exists a cut of size m by 2. Okay. So, its existence is proved. That means, I mean, if all the cuts were of size less than m by 2, then invariably the expectation, if you randomly choose a cut, the number of, if the expectation is less than m by 2, if you had randomly chosen a cut, that will have edges strictly less than m by 2, and therefore, the expectation cannot be greater than m by 2. How do we calculate the expectation of the number of edges in the cut? So, let us do the following. So, this is our randomly chosen cut, and this is, let us say, the edges in the graph. We will have a random variable x e for each e belonging to the edge set. We will have a random variable x e, and this x e is 1 if and only if e is a cut edge. So, let us look at the random variable x. X is just the sum of all edges belonging to, sum over all edges belonging to E x e. Okay, this will give us, this sum over all edges x e will give us the number of edges that are there in the cut. We are interested in computing the expectation of x. So, this is equal to, by linearity of expectation, you can take the expectation inside. So, this is just sum over E belonging to E expectation of x e, and expectation of x e. So, what is the probability that one edge is a cut edge? Well, it has two vertices u and v. Let us say u was in one side, it was chosen to be in one side. Only if v is in the other side, we will have this as a cut edge, and that happens with probability half, because in order to choose the side for vertex v, we would have tossed a coin, and the probability of that returning the suitable side is just half. So, this expectation is going to be half, this is going to be half. So, this is going to be sum over all edges half. So, that is going to be equal to m by 2. So, we know that the expectation of x is m by 2, therefore, there must exist a cut of size greater than or equal to m by 2. So, that brings us to the end of the first lecture. We will see more advanced examples in the coming lectures. Thank you.